Series of lectures, we will learn the design of the caches. And for this series of lectures, they correspond to the chapter 7 in the Computer Organization and Design textbook, and they also corresponds to the Appendix B in the Computer Architecture textbook. In these lectures, we will learn mainly three topics. The first one is the cache placement policy. Then we're going to learn cache replacement policy. And in the end, we will learn write strategies. How does the cache handle the write operations? Let's first look at cache placement policy. What is cache placement policy? Cache placement policy specifies for a cache line. Cache placement policy specifies which frame should this cache line be stored. So given a cache that has thousands or even hundreds of thousands of cache lines, slots and frames, where should a particular cache line be stored? The answer is determined by the cache placement policy. There are three main types of cache placement policies, which are the direct mapped cache, fully associative cache, and set associative cache. For majority of the caches that we have in real life, they're mainly set associative. All the above three cache line placement policies, cache line addresses are used to determine which frame or which slot a cache line should be stored to. Therefore, before we learn the exact internal algorithm of each cache placement policy, let's first look at cache line addresses and see how these addresses are handled or manipulated by the hardware, the cache hardware. Consider a cache line without loss of generality. Consider a cache line with the size 2s. And here S indicates the cache line, the size of the cache line. For example, if we're looking at a 64-byte cache line with 64 bytes, it effectively the length of this cache line is effectively 2 to the 6 bytes. Therefore, S is going to be 6 in this case. Similarly, if we have a cache line of 32 byte long or 32 bytes, then this cache line has 2 to the 5 bytes. Therefore, the S is going to be 5 in this case. So S here effectively indicating the length of the cache line. And for a cache line, for any cache line with a size of 2s, the last S bits of the address of this cache line in the binary format will always be 0. So let's look at one example. Let's look at a few examples. So here, this is our memory. And in this memory, as we have discussed before, we partition the memory into an array of cache lines. So each row here indicates a cache line that is 64 bytes long. And these three cache lines are starting with, we're focusing on the first three cache lines, and these three cache lines starts with three addresses. The first cache line starts with address 0 and it ends with address 64. So the first byte of this cache line gonna start has an address of 0, which indicates that this cache line starts with 0, with the address of this cache line is 0. And the last byte of this cache line has an address of 63. For the second cache line, its beginning address is going to be 64. So the first byte of the second cache line has an address of 64, and which also indicates that this cache line starts at address 64. And the last byte of this cache line has an address of 127. For the third cache line, the first byte starts with an address of 128. So this cache line also starts with the address of 128. And this cache line ends with address. The last byte of this cache line is 191. And if we examine the beginning address of these three cache lines, we will see the last S bits of them are always going to be 0. So for example, the first cache line its address is 1, and which indicates that its binary format, if we translate the first cache line address is 0, if we convert this into binary number, we can easily see that they have all zeros. So the last 6 bits, they're all zeros. Of course, because this number is 0, right? And the second cache line is address. It starts with at address 64, and if we converted this number into binary format, we're gonna have 01, 00, 0000, and this is also all zeros. And similarly, for the third cache line, its beginning address is 128, and the binary format of it is 10, 00, 00, 00, and 0. So again, we have all zeros for the address, beginning address of the last 6 bits. The last 6 bits of the third cache line of the address of the third cache line are also all zeros. If we can continue to check more cache lines, and the same observation holds. The last bits, the last 6 bits of all these cache lines, of the beginning address of all these cache lines, are always going to be 0. However, for an arbitrary piece of data that is located within the cache line, the last S bits cannot always be 0. And actually, for most of them, the last S bits are not 0. Now let's look at a more detailed example. Let's look at more detailed cache lines in the memory. Here again, we're focusing on the first 3 cache lines. The first cache line starts with address 0, the second one starts with address 64, and the last one starts with address 128. And the first one ends with address 63, the second one ends with 127, and the last one ends with 191. Okay. And for the addresses within this cache line, for example, for the first cache line, the bytes the first byte is going to have a address 0, the second byte going to have address 1, and the third byte going to have an address 2, and the last byte is going to have an address of 63. And for an address in between, for example, the address of 31, the byte with address 31, the binary format of this address is 0B, 00, 01, 1, 1, 1, and 1. So the last 6 bits are 0 and 5 ones, which are obviously not 0. And let's look at another byte. For example, this byte with the address 60. For this byte, the binary format of the address is 0B, 00, 1, 1, 1, 1, 0, 0. So again, the last 6 bytes are not 0. Similarly, let's look at the second cache line. Let's look at, for example, let's look at byte 72. 72 has the binary format of 72 is 0B, 01, 00, 1, 0, 0, 0. So the last 6 bits are 0, 0, 1, 0, 0, 0. So it's not all zeros, right? So this is not all zeros as well. So all of them are not all zeros. And let's look at another byte. For example, let's look at 111, the address with all ones. And this decimal number in the binary format is 0B, 01, 10, 11, 11. So last 6 bits. So for this number, the last 6 bits, so this for 1111, the last 6 bits are not all 0. Last, let's look at the third number. Let's look at the third row, the third cache line. This time let's try the second byte in the third cache line, whose address is 129. And for this byte, is binary format. The address 129, the binary format is 10000001. So the last 6 bits are 5 zeros with a 1. It's not all zeros. And let's look at the third another value. For example, we're looking at 167. And the binary format of this number 167 is 10100111, which again, they are not all zeros, the last 6 bits. So for a byte that is actually located within the cache line, the last 6 bits are not always zeros. What I want to draw your attention to is that if you look at actually these two addresses in the first cache line, you can see that although the last 6 bits are different, the first 2 bits are always the same. They're always 0. And for the second cache line, the first 2 bits are for the second cache line, the 2 bytes within the second cache line, the first 2 bits of these 2 bytes are also same. They're always 0, 1. And for the third cache line, for these 2 bytes within the third cache line, the first 2 bits of their addresses are also the same, 1, 0 as well. So effectively, if you look at the absolute index number of these cache lines, you'll see that these 2 bits matches the index number of these cache lines. So for the first cache line, if we convert it to the index of the cache line, if we convert this into the index of the cache line, see that this is our first cache line, and the beginning address is 0. So this is the index of this cache line is going to be 0. And then for the second cache line, its index obviously is 1, and its beginning address is 64. And for the third cache line, the index of the third cache line is going to be 2, and its beginning address is 128. And the fourth cache line, obviously, its index is going to be 3. And if you look at these 2 bits happens to be 0, right? These 2 bits happens to have a value of 0, which is exactly the same as the index of the first cache line, which is 0. And for the second cache line, the bytes within it, the address of the bytes within it, it also begins with 2 bits that has a value of 1. So this is value 1, this 01 value is 1, which also corresponds to the beginning, the index of the second cache line. And similarly, for the third cache line, the first 2 bits of the addresses of the bytes within the third cache line, they also start, the first 2 bits start with 10, which the first 2 bits are 10, which corresponds to value 2, and this also corresponds to value 2, indicating that this value 2 here also corresponds to the cache line, the index of. Summarize this observation into the addresses of any piece of data. Let's say here we have the address of an arbitrary piece of data, and this is the address of any data. And within this address, we can partition this address into 2 parts. The first part is going to be S bits. And we call this S bits offset. And it indicates that for this piece of data, what is this location or its offset within each cache line. This S bits indicating the relative location of this particular piece of data, the relative location of this particular piece of data within its own cache line. And for the rest of these addresses, we call it corresponds to the index of this cache line, or we call the rest of this cache line index. And this cache line index directly corresponds to the index of each cache line as we have drawn here, 0, 1, 2, 3, and this goes on. So for any piece of data, for any for the address of any piece of data, we can partition it into two parts. The first part is going to be the last S bits, which corresponds to the relative location or the offset of this piece of data within its own cache line. And for the rest of the bits, they are called the cache line index, which directly corresponds to the index, of that cache line. If you take out the first bits, then you can directly get the index of this cache line, that contains this piece of data.